Alrighty, welcome back to 2.9. This is just going to be a summary of all of the Unit 2 material that we've covered. So consequently, I'm going to try to move fairly quickly through this material. It is there are a lot of examples in this section, so we'll try to get through it as fast as we can, and hopefully give you a pretty good summary of what we've talked about. So make sure that your notes are ready to go and that you're ready to dig in, and we'll get to it. So in the first few sections of this unit, we talked about just the basics of probability in sections 2.1 through 2.4. So we'll start off by reviewing that material, and then we started talking about probability distributions, and we did that in 2.5 through 2.7, and then finally in 2.8 we talked about sampling distributions, and that was really the section that the entire chapter was building up to. So let's get to it, and we'll talk about the basics of probability. So the basic notion of probability is that the probability that A occurs is the number of ways that A can occur divided by the total number of possibilities. For example, a bag of marbles contains 15 blue, 17 green, and 12 clear marbles. If a marble is chosen at random, what's the probability that it's green? Well, the probability that it's green is going to be the number of green marbles in the bag divided by the total number of marbles in the bag. Okay, so you can type that into your calculator. 15 plus 17 plus 12 comes out to 44. And if you want, you can change that into a decimal, or you can try to reduce the fraction. This one's not going to reduce, but as a decimal, this would be approximately 0.386. When you're showing your work on probabilities, I want you to write out the probability notation, and I also want you to show your work, okay? Obviously, I want the answer, but don't just give me the answer. Give me these steps as well, okay? Now, sometimes it takes a little bit of work to figure out how many ways something can happen, and so we introduced counting techniques back in section 2.1. And when we did that, we had this flow chart to help us kind of decide what counting technique we should use. Okay, so questions you should ask yourself, first of all, if you're trying to count up something, is repetition allowed here? And if so, you should use exponents. If not, then you should ask yourself a follow-up question. Does the order matter? If so, you use a permutation, and if not, you use a combination. There are other kinds of counting techniques, but for this class, that's going to be good enough. So, for example, suppose a NASCAR race has 43 drivers competing. If you know nothing about NASCAR, what's the probability that in 5 guesses you can choose the top 3 finishers, first, second, and third, in the correct order? Okay. So the probability that I'll just call it W for win, okay? The probability you win is going to be the number of guesses you get divided by the number of guesses possible. So number of guesses you get divided by the number of guesses possible. Now, the numerator there is pretty straightforward. You get 5 guesses. The denominator is going to take a little bit more work, though. The number of guesses possible. So if we want to choose the top 3 finishers, then, well, we should ask ourselves, first of all, is repetition allowed? Does it make sense to choose the same person to finish in both first and second place? And I think the answer there is clearly no, right? So repetition's not allowed. So now we're on to this question. Does the order matter? And here I would say the answer is definitely yes, because Bob getting first place and Sally getting second place is a totally different scenario from Sally getting first place and Bob getting second place. So the order matters, and that means we're going to use a permutation. So right off the bat, I know I'm going to be using a permutation. I have 43 racers to choose from, and I need to choose the top 3. So it's going to be 43 permute 3. In the Desmos calculator, in the scientific calculator, you would just type it in as NPR, and then you would do 43 permute 3. Okay, so that comes out to 74,046. Now, of course, we want the probability and the probability was going to be 5 out of that number, right? NPR 43, choose 3. And that's a pretty small number, right? The likelihood you get it right is pretty small, about 6.75 times 10 to the negative 5. Oh, 6.75 times 10 to the negative 5. That's the scientific notation for the answer. If you want the standard notation, then you need to take this decimal point right here and move it 5 times to the left. So you move it once, and then you move it 4 more times, and so you're going to have 4 zeros, right? This is going to be 0.1, 2, 3, 4 zeros, and then a 675. Okay, so that's the basic notion of probability. Now, we also had compound probabilities. Compound probabilities are when we're trying to figure out the probability of 2 or more events occurring. And when we're trying to figure out the probability of 2 or more events occurring, we need to pay attention to the conjunction that's used. If it's an or probability, we should think addition. If it's an and probability, we should think multiplication. Let's practice. So number 3 here says, a card is chosen from a standard 52 card deck. Let A be the event that the chosen card is a face card, and let B be the event that the chosen card is black. And then we're asked to compute a whole bunch of stuff, right? So probability that A occurs. Well, A is the event that we choose a face card. There are 3 face cards in each suit, right? And there are 4 suits. So that means there's going to be 12 face cards in the deck in total. And if you're unfamiliar with cards, you're welcome to use on the test, you're welcome to use like a picture of a deck of cards, right? In fact, I'll put one on Canvas for you. So if you need to have a picture of a deck of cards out in front of you, then by all means, right, bring out a picture of a deck of cards. But there are going to be 12 face cards in that deck, okay? 12 face cards out of 52 cards in total. And so you can type that into Desmos. As a fraction, it would reduce to 3/13. And if you wanted to give a decimal, it would be 0.231-ish. Okay. Part B says to compute the probability that the card is black, right? P of B, probability of black. Well, there are 26 black cards in the deck out of 52 cards. That will reduce to 1/2, which as a decimal is 0.5. We've probably computed that probability 1,000 times. Let's look at part C. Part C says to compute the probability of A given B. In other words, we want the probability of choosing a face card given that the card is black. So if we're given that the card is black, then it's like the red cards don't even exist. It's like there are only 26 cards to choose from, right? Because we're given that the card is black. And out of those 26 black cards, the question now is how many of those are face cards? And the answer would be 6. There's a jack, queen, and king of clubs, and a jack, queen, king of spades, right? So 6 face cards in total. You can punch that into your calculator, and that would reduce to 3/13, okay, which as a decimal would be 0.231, just like we saw in part A. Now part D says compute the probability of B given A. In other words, the probability of choosing a black card given that the card is a face card. So now we're restricting our attention to just the face cards in the deck, right? So if we're going to do that, then we don't have 52 cards to choose from. We only have the face cards to choose from. There are only 12 of those. Now, of those 12 face cards, how many of them are black? Well, it would be 6, right? As we've seen already, there are 6 black face cards. So probability B given A would be 6 out of 12. That reduces to 1/2, which is 0.5. Notice right off the bat that the probability of A given B is not the same thing as the probability of B given A. However, it is the case in this particular scenario that the probability of A is the same as the probability of A given B, and the probability of B is the same as the probability of B given A. What that means is that events A and B are independent, right? The occurrence of one does not affect the probability of the other event occurring. That's not something I'm going to drill down too hard on. Let's move forward. So part E asks for the probability of A and B. So this is the probability that the card is a face card and black, okay? But notice that we're not making any assumptions about what the card is. We're not given any information about the card. So we're not restricting our attention to any subset of the deck. We're looking at the entire deck, all 52 cards. Now, how many of those 52 cards satisfy both those conditions of being black and being a face card? And as we've seen in parts C and D already, there would be 6 of those, right? There are 6 black face cards. So we could punch that into our calculator. And as a fraction, we would get 3 out of 26 reduced. As a decimal, we would get 0.115 approximately. And then finally for part F, we want to compute the probability of A or B. So probability of A or B. Now, there are a couple ways you could do this. You could do this by inspection. You could just look at the deck and count up the number of cards that are either face cards or black, okay? Being careful not to double count the cards that are both. Or you could use the formula, right? Probability of A or B, if we use the formula, is probability of A plus probability of B minus the probability of A and B. And I kind of like the formula. To me, it makes it a little bit easier since I've already done all of the work already. Probability of A was 12 out of 52. Probability of B was 26 out of 52. But then the probability of A and B was 6 out of 52. I'm using the unreduced versions because it's easier to do the math that way. But I guess if you're going to use Desmos anyway, it doesn't really matter, right? But let's see what we get. So we're going to have 12 plus 26 minus 6, all out of 52. And that comes out, as a fraction, that would come out to 8/13, or as a decimal, it's approximately 0.615. Okay. So that's how compound probabilities work. I think I have a couple more examples for you, like this one here where we're looking at a contingency table. So let's practice doing probabilities when we have a contingency table to deal with. This is supposed to represent the survival data for the Titanic voyage, so kind of fun. Maybe fun is the wrong word, but okay. So we have men, women, children, and then we have whether or not they survived or died, right? Okay, well, let's take a look at the probabilities we're supposed to compute. It says, suppose a passenger is selected at random. Let S be the event that the passenger survived, and let M be the event that the passenger was a man. Compute the following. So in part A, we want the probability the passenger was a man. Well, the probability the passenger was a man would be the total number of men on the ship divided by the total number of people on the ship. There were 2,224 people on the ship in total, and out of those, 1,690 were men. Okay, so you could punch that into Desmos, and let's just give decimals because these numbers are so big. It's hard to make sense of them as fractions. So as a decimal, this is approximately 0.760 if we round to 3 decimal places. Okay, part B. What's the probability that the individual survived? Okay, well, the probability the individual survived would be the number of survivors divided by the total number of passengers. Total number of passengers is, once again, 2224. Okay, total number of survivors would be 711. Okay, so we punch that into our calculator, and we get about 0.320 if we round to 3 decimal places. Okay, let's look at part C. Part C asks for the probability the individual survived given that he was a man. Okay, So now we're restricting our attention to just the men on the ship, right? So just to these individuals. It's like the rest of the individuals don't even exist. Okay, so restricting our attention to just the men, what is the probability that the individual survived? And that would be the number of male survivors divided by the total number of men. Okay, so if we type 338 out of 1690 into our calculator, oh, that comes out to exactly 20%, which is kind of interesting. Okay, I'm just putting a couple extra zeros there to indicate that I've rounded to 3 decimal places, but yeah, that's really interesting. Okay, well, let's look at the probability that the individual is a man, given that he survived. Okay, well, so this is sort of the opposite scenario, right? Because now we're going to restrict our attention to the survivors, right? We're going to restrict our attention to this top row, and it's as if the rest of the individuals don't exist. Okay, so out of that top row now, what's the probability the individual is a man? Well, it would be there were 338 men in that top row out of 711 people in the top row in total. And that comes out to about 0.475. Okay, so once again, we can see that probability of S given M is not the same thing as the probability of M given S. But unlike the previous example, notice that the probability of S given M and the probability of S are not the same thing in this example, right? And the probability of M and the probability of M given S are also not the same thing in this example, which tells us that M and S are not independent in this case, right? In other words, whether or not you survived depended on which of these groups you belonged to, okay? If you were in the male group, then the likelihood that you survived is smaller, right? It's smaller than it is generally, right? So this is how small it is, or this is how likely it is for someone to survive generally. This is how likely it is for someone to survive if they were a man, right? Much smaller. Okay, let's take a look at a couple more. Compute the probability of S and M. So we want the probability that the individual survived and was a man. Okay, notice that this time we're not given anything. Okay, we're not given that the individual belongs to a certain category. We're just asking out of all of the individuals, okay, out of all the individuals, what's the probability that the individual was both a survivor and a man? Both a survivor and a man, right? That would be 338. 338 out of 2224. That comes out to approximately 0.152. Now, by the way, I failed to mention this on the previous example, but we do have a formula for this as well, right? Probability of S and M is probability of S times probability of M given S. So if you like the formula, you can use the formula. Probability of S, we said earlier, was 711 out of 2224. And probability of M given S, we said, was 338 out of 711. And you can punch that into your calculator as is, but what I'll point out to you for those of you who are familiar with cross-canceling is that you end up with 338 out of 2224, just like we got up here by inspection. But you don't have to do it this way if you don't want, because you can jump straight to the answer just by looking at the chart, right? It works perfectly fine. Part F, compute the probability of S or M. So probability the individual is a survivor plus the probability that the individual is a man minus the overlap, okay? Because we don't want to double count those individuals who belong to both categories. So this is 711 out of 2224 plus 1690 out of 22, 24. And by the way, I'm just getting these numbers from my previous work. This was part B, this was part A, and then minus probability of both, right? 338 out of 22, 24. I'm getting that from part E. Okay, and then you just type that into your calculator and see what you get. So that comes out to about 0.928. Alrighty. One more example of basic probabilities, and then we'll talk about some probability distributions. This one says a jar contains 30 marbles. 10 are green, 7 are blue, 8 are clear, and 5 are red. If you draw one marble from the jar, if you draw one marble from the jar, what is the probability that it's clear? So probability that it's clear. There are 8 clear marbles out of, it looks like 30 marbles in total. Okay, we were given the total in this example. But if you wanted, you could also get that total by adding these up. 10 plus 7 plus 8 brings us up to 25, plus 5 more is 30. Okay, so anyway, probability of marbles clear, 8 out of 30. As a fraction, that would reduce to 4/15. And as a decimal, that's about 0.267. That's just my dog. No, don't mind him. He'll survive. Okay, part B. If you draw 3 marbles from the jar without replacement, what is the probability that all 3 are clear? So when it says without replacement, remember that means you do not replace the marbles. You don't put them back in the jar before you pick the next marble. So if we're going to draw 3 in a row without replacing them, what's the probability that all 3 are clear? All 3 clear. Okay? Well, the probability that the first one is clear is 8 out of 30, as we just saw in part A. Now, having chosen a marble that was clear, we only have 7 clear marbles left and 29 marbles overall to choose from for our next draw. Okay, and then for our third draw, we'll only have 6 marbles left to choose from and 28 marbles left in the jar, because remember, we're not replacing them. So we can type that into our calculator. Comes out to about 0.014. And then finally, part C asks, if you draw 3 marbles from the jar with replacement, what's the probability that all 3 are clear? So this time we will replace the marbles back into the jar. All 3 clear. Okay, so on our first draw, there are 8 clear marbles out of 30 marbles in the jar. And on our second draw, there will still be 8 clear marbles in the bag and 8 clear marbles in the jar and 30 marbles overall in the jar, because we replaced that first one back into the jar before making our second draw. And same thing with the third draw. There will still be 8 clear marbles and 30 marbles in total. So that's 8 out of 30. If you want to be fancy, you can just call it 8 out of 30 cubed, and that would work just fine. Either way, you should get 0.019 approximately. Okay, so that pretty much covers the basics, kind of the basic notion of probability. The next major topic was probability distributions. So let's review that, okay? A random variable x is a variable that has a single numerical value determined by chance for each outcome of a procedure. A probability distribution is a pattern of how probabilities are spread across all possible outcomes for a random variable. And a probability density function is part of that description, okay? It's a rule that describes all of the possible values that a random variable can take on and assigns them each a likelihood. There are discrete distributions, that means that x would be counted, and there are continuous distributions, which means that x would be measured. In either case, we describe a probability distribution by giving it shape, center, and spread, okay? So for the shape, we could just look at a probability histogram. For the center, we're going to report the mean, which is the same thing as the expected value. Okay, and for the spread, we're gonna report the standard deviation. Now let's just review a little bit about the mean and the standard deviation. If you have a discrete variable, the mean, which is the same thing as the expected value, is the sum of all the x times p of x's. So if you have a little probability distribution like this, where you have some values, right? Some values in each of these places. Oh, I should have given them different names to make it easier. Let me just call it like A, B, C or something. Then to compute the mean, we would do x times p of x, x times p of x, x times p of x, and then add those up, right? That's how you would get the mean, which is the same as the expected value. For the standard deviation, you have a similar formula for discrete variables. For continuous variables, we also have a formula, but we're not going to use it because it would require calculus. So it's kind of beyond the scope of this course, okay? So you don't have to worry about those ones. I would also point out that we get shortcuts, okay? So instead of having to use this formula for the mean or this formula for the standard deviation, if we can identify the specific kind of variable that we're working with, then we get some shortcuts, right? So here are the special distributions that we talked about, okay? So for discrete distributions, we have the binomial and the Poisson. This is how you compute things in Desmos for those two distributions, and here are the means and standard deviations for those two distributions, okay? For continuous distributions, the special ones we talked about were the normal, the uniform, and student's t distributions, okay? So again, this is how you would handle these in Desmos. And then these are the means and standard deviations, okay, for each of those specific kinds of random variable. Much nicer when we have those shortcuts, right? Out of all of these 5 distributions that we've listed above, the most important are the binomial and the normal. We spent a section on each of those, okay? And then also I would draw your attention to the fact that on Canvas, there's a Desmos probability procedures handout that you're welcome to use that has all of this information on it, okay? So let's walk through a few examples. A fair coin is tossed 6 times. Let x be the number of times heads is flipped. Okay. Part A says, is x binomial, normal, or neither? Okay, because if it's binomial, we'll use the binomial distribution. If it's normal, we'll use the normal distribution. If it's neither, well, I guess we could ask ourselves whether it's Poisson or uniform. But if it's Poisson or uniform or t, I will tell you point blank in the example that it is Poisson or t or whatever. So really, and notice that number 5 doesn't say, right? It doesn't say. So we can rule all of those out. So it's either binomial, normal, or neither. Well, in order for it to be binomial, we would have to be counting up the number of successes, right? And I think that's exactly what we're doing. X is the number of times that we flip heads out of 6 tosses, right? Out of a fixed number of trials. So I think we're counting up the number of successes here in a fixed number of trials. That definitely makes this binomial. And what that means is that when we have to do something like part B, what's the probability the coin comes up heads exactly 4 times? We can use the binomial distribution in Desmos to do that. When you use the binomial distribution, you have to put in the number of trials, which is 6 in this case, and the probability of success, which we weren't given, but we can figure that out. If it's a fair coin, the probability of flipping heads is 50%. Okay, and then we want the probability that we flip heads exactly 4 times. Now, in Desmos, there isn't an equals region. So in order to do this, what we actually have to do is put it in this way. Okay, so let's head over to Desmos and see what that looks like. So we're going to use the binomial dist. N was 6, P was 0.5. And we can zoom in on that and also compute a cumulative probability. We want the probability x is exactly 4, so between 4 and 4. Okay, so that comes out to about 0.234. If you need more decimal places, you can always click on that little down arrow to get more. But I'm going to go ahead and round to 3 since that's what I've been doing in this section, 0.234. Okay. Part C says to compute and interpret mu sub x. Well, for a binomial distribution, mu sub x is n times p. And n we already said was 6. P we already said was 0.5. So this is 6 times 0.5. 6 times 0.5 is 3. So that's the mean. The interpretation would be that we expect to flip heads 3 times. If we toss a fair coin 6 times, we expect it to come up heads 3 times, right? Let me say, out of our 6 flips, we expect to get heads 3 times. Okay. And then part D, compute sigma sub x. Well, since this is a binomial distribution, sigma sub x is the square root of n times p times q. Okay, so that's going to be the square root of 6 times 0.5. And now remember, q is always 1 minus p. So if p is 0.5, q is 1 minus 0.5. 1 minus 0.5 is 0.5. Okay, so we can type that into our calculator. And we should get approximately 1.22. Okay, let's look at another one. The reading speed of 6th grade students is approximately normal, with a mean speed of 125 words per minute and a standard deviation of 24 words per minute. Let x be the reading speed of a 6th grade student. Is x binomial, normal, or neither? Well, this time it's a dead giveaway, right? Because x is supposed to represent the reading speed of a 6th grade student, right? And we were told in the first sentence that, well, the reading speed of a 6th grade student is normally distributed, right? So it's got to be normal. Part B, what's the probability that a 6th grade student reads fewer than 130 words per minute? Well, since x is normal, we'll use the normal dist. When you use the normal distribution, you have to put in the mean, which is 125, and the standard deviation, which is 24, right? We got those from here. The mean is 125, standard deviation is 24. And we're looking for the probability that the reading speed is fewer than 130, okay? Less than 130. Let's see what we get. So we want a normal dist with a mean of 125 and a standard deviation of, I don't remember, 24. Okay. Let's zoom in on that. And we're looking for the probability x is less than 130. So that comes out to 0.583. There's a 58.3% chance, right? Okay, part C says compute and interpret mu sub x. Well, for a normal random variable x, mu sub x is just going to be mu. It's just going to be the mean of the distribution, which we've already said was 125. There's really no computation to be done. It was just given to us, right? 125. The interpretation would be that this is how fast we expect a 6th grade student to read, right? Because it's the average reading speed. We expect a 6th grader to read 125 words per minute. Part D says compute sigma sub x. Well, again, for a normal random variable x, sigma sub x is just going to be sigma. It's just going to be the standard deviation of the distribution, which we were told was 24, right? We were given that information there. So that's all there is to number 6. Let's move on. Look at another one. Number 7 says a pair of fair dice is thrown. Let x be the sum of the dice. Okay, so again, we're confronted with this question, is x binomial, normal, or neither? And I hope you understand the purpose of this question is not to try to trick you. The purpose of this question is to help you correctly identify what kind of variable we have, because if it's binomial, we'll use the binomial distribution. If it's normal, we'll use the normal distribution. If it's neither of those things, and it's also not Poisson or uniform or something like that, then we'll just have to figure out the probability ourselves, right? So let's see, is x binomial, normal, or neither? Well, in order for it to be binomial, we would have to count up the number of successes. And I don't think that's what's happening here. X is just the sum of the dice. Okay, so we're not counting up the number of times something happens. We're just recording the sum of the dice. Is x normal? Well, it's not normal either. The problem doesn't say it's normal for one thing, but for another thing, a normal distribution is a continuous distribution, which is something that's measured. The sum of the dice is not measured, it's counted, right? When you roll a die, you count up the number of pips, right? The number of little dots on the die. So we get these values by counting, which means x is a discrete distribution, so it's not normal. So x is neither binomial nor normal, right? It's neither. And as I've said before, if it were Poisson or uniform, I would tell you that. And since I didn't tell you that, we can just say, well, this is not any of our special distributions. So when we go to answer part B, what is the probability the sum of the dice is 5? We'll just have to figure that out ourselves, right? The probability that we roll a 5. So the probability we roll a 5 is going to be the number of possible rolls, the number of ways to roll a 5 divided by the number of possible rolls. Now, we've looked at the outcomes when we roll a pair of dice before, and so you may recall that there are 36 possible outcomes. If you didn't recall that information, then you might go back to section 2.2, and we actually listed out all of the possible outcomes in section 2.2. But there are 36 possibilities here. Now, out of those 36 possibilities, in how many ways can we roll a 5? Well, that could happen if we roll a 1 and a 4, or if we roll a 2 and a 3, or if we roll a 3 and a 2, or if we roll a 4 and a 1. It's not possible to roll a 5 and a 0, or something like that, right? So those are the only ways that this could happen. So it looks like there are 4 of them, right? So the probability the sum of the dice is 5 would be 4 out of 36, which of course reduces to 1/9. And as a decimal, it would be approximately 0.111. Okay. Now part C says to compute and interpret mu sub x. And oh boy, once again, this is an unfortunate scenario because we don't have because x in this case is not a special distribution, and so we don't have a shortcut for computing mu sub x. We have to use the long version of the formula, right? We have to say, well, mu sub x is going to be the sum of x times p of x. In order to do that, I think it's going to be best if we actually list out all of the possible values together with their corresponding probabilities. So I'm going to try to squeeze this into the left margin, and I'm going to make a little chart. Okay. So let's think. What's the smallest x could be? Well, again, x is the sum of the dice. The smallest you could ever roll would be a 2. And that would be if you roll a 1 and a 1, right? If you roll a 1 and a 1, then the sum is 2. You could roll a 3, a 4, a 5. What's the largest x could be? Let's think about that for a second. If both of the dice are a 6, then the sum of the dice will be 12. So I think the largest x would be 12. So these are all the possible values of x. Now let's think about their probabilities, okay? The probability that x equals 2, well, there's only one way to get a 2, and that's to roll a 1 and a 1, okay? One way to get a 2 out of 36 possibilities. To roll a 3, I think there are 2 possibilities. You could roll a 1 and a 2, or a 2 and a 1, right? So there are 2 out of 36. The probability of rolling a 3 is 2 out of 36. Probability of rolling a 4. Well, for a 4, you could roll a 1 and a 3, a 2 and a 2, or a 3 and a 1. Okay, there are 3 of those. And again, if this is too confusing for you, then by all means, bring out your 2.2 notes and take a look at that chart that we put together where we listed out all of the possibilities. Probability we roll a 5 is 4 out of 36. Okay, we just saw that in part B. And I think you can start to see a pattern, right? It's going 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 3. So it's probably 5 out of 36, and then 6 out of 36. But the pattern does stop eventually, because if you think the probability of rolling an 8 is 7 out of 36, that's not going to be correct. Okay, so let's think this through. I'll leave it to you to verify that the probability of rolling a 6 and a 7 are 5 out of 36 and 6 out of 36. But it does start to come down from there, because to roll an 8, let's think, to roll an 8, we could have a 5 and a 3, a 6 and a 2, a 6 and a 2, a 5 out of 3, a 4 and a 4, a 3 and a 5, or a 2 and a 6. So there are 5 possibilities, 5 ways to roll an 8. Okay, and then there are going to be 4 ways to roll a 9, and 3, 2, 1. And again, I know I'm going through this really quickly, so I'll leave it to you to verify that that is all correct. Okay, but that's just a step in the right direction, because what we really came here to do was to compute the mean. So let's get to that now. Let's try to compute the mean of this distribution. So we're going to do the sum of all the x times p of x's. So it's going to be x for our first possible value. It's going to be 2 times 1 out of 36. Okay, and then for our next pairing, it's going to be 3 times 2 out of 36. Okay, and we're going to add these up, right? So then for the next one, it's going to be 4 times 3 out of 36. And for the one after that, it's going to be 5 times 4 out of 36, right? And so forth. So I'm going to stop trying to color code these so I can go a little quicker. 6 times 5 out of 36, 7 times 6 out of 36, 8 times 5 out of 36, 9 times 4 out of 36, and I'm running out of room, so I'm just going to say dot, dot, dot. We're going to continue this pattern until we get to the end, right? 12 times 1 out of 36. And let me go ahead and type that into my calculator. So if you type all of that into your calculator, you get 7. Exactly 7. As you can see, we really don't like to use this long version of the formula, which is why we spend so much time asking ourselves these questions, because we hope beyond hope that x is some kind of special distribution, so that we can use some shortcuts. But anyway, this is the long way to do it, and that's the only way to do it in this case, because x is none of our special distributions. We were asked to interpret mu sub x, so the interpretation would be that we expect to roll a 7. Okay, if we roll a pair of fair dice, we expect the sum of the dice to be 7. Okay, let's do, I think, just one more like this, and then we'll be talking about sampling distributions. But number 8 here says, suppose that a recent poll found that 36% of adult Americans like cats. A random sample of 10 American adults is surveyed, and the participants are asked how they feel about cats. Let X be the number of people surveyed who like cats. Part A says, is X binomial, normal, or neither? So what is X? X is the number of people who like cats. So we're counting up the number of people who like cats. It sounds to me like we are counting up the number of successes. So, yes, I would say that X is binomial, right? So X is binomial. So then when part B asks us to compute the probability that exactly 4 of the people surveyed like cats, we're just going to use the binomial distribution to do that. Our sample size was 10. We had a random sample of 10. Okay. And the probability of success was 36 because 36% of adults, American adults, like cats. Of course, you have to put that in as a decimal. And then we're going to look for the probability that exactly 4 liked cats. Okay, so when we go to put this into decimals, we'll have to write it this way. Let's see what we get. Binomial dist, sample size of 10, probability of success of 0.36. And let's zoom in on that and compute cumulative probability. We want the probability X is between 4 and 4. So there you go, right? The probability X equals 4 is about 0.242. Okay, part C. Of the 10 people surveyed, how many would you expect to like cats? Ooh, okay. So when they ask how many would you expect to like cats, as we've been noticing on the previous examples, right? The mean is the same as what we expect to occur, right? It's the same as the expected value. So how many would we expect to like cats? Well, that's going to be the expected value, okay? Which is n times p, right? It's the same thing as the mean, n times p. N we said was 10, p we said was 0.36, and 10 times 0.36 comes out to 3.6. Now here we have to be a little bit careful because if somebody asked you, how many people in your survey do you expect to like cats? You would not say 3.6. Okay, because it doesn't make sense for 0.6 people to have an opinion one way or the other, right? You would round this to the nearest value that makes sense, right? So we would say 4. We would expect about 4 people to like cats. But notice that there's a follow-up question here, right? So this is if 10 people are surveyed. If n equals 10, right? But then the follow-up question is, well, what if 100 people were surveyed, right? If n equals 100, then the expected value now is going to be still n times p, but n is 100 and p is still 0.36, but 100 times 0.36 is 36. If somebody asked you how many people would you expect to like cats and you said 36, that's an answer that already makes sense, so there's no rounding necessary for that follow-up. Okay, so that will do it for probability distributions. Let's talk about sampling distributions. So we talked about 2 sampling distributions. We talked about the sampling distribution of x bar, okay, sampling distribution of x bar, and then we talked about the sampling distribution of p hat. What's incredible is that both x bar and p hat are normally distributed. Okay, they're both normal. They both have a bell-shaped distribution as long as certain conditions are met. In the case of x bar will be normal as long as the population you're drawing from is normal, or you have a large sample size. As long as one of those conditions is met, then we can conclude that x bar is normal. For p hat will be normal as long as n times p times q is bigger than or equal to 10. There was also a second condition that n had to be less than or equal to 0.05 times capital N, but that condition is really hard to check because we're usually not given the population size, capital N. Anyway, I'm not going to ask you to check these conditions anyway, but this is what the central limit theorem says, right? That both of these things are normally distributed, which is kind of crazy. The center of the sampling distribution of x bar is just going to be the population mean. And that makes sense, okay? Because some of our sample means will underestimate the population mean and some of the sample means will overestimate it. But when you take the average of all the sample means, you should get the population mean. For the sampling distribution of p hat, the mean is going to be the population proportion. And again, that makes sense because some of our sample proportions, right, some of our p hats are going to underestimate the true population proportion p, right? So some of the p hats underestimate p and some of the p hats overestimate p. But when you take the average of all the p hats, you should get exactly p, okay? As for the standard deviations, those formulas are a little bit more opaque. But the standard deviation of our sample means is going to be the population standard deviation divided by the square root of our sample size. And the standard deviation for our sample proportions is going to be the square root of PQ over N. When you're making your cram sheet, I think that those would be good things to have on it, right? Let's take a look at a couple examples. Okay, so number 9 here says the heights of unicorns are normally distributed with mean 63 inches and standard deviation 3 inches. Part A asks, what is the probability that a randomly selected unicorn is more than 65 inches tall? Part A is not a sampling distribution question because Part A is not asking us to compute the probability that a sample mean is such and such. Instead, Part A is just asking about a single unicorn, right? Just one unicorn. And we know that the heights of unicorns are normally distributed. So we'll use the normal distribution to compute this probability. Normal dist with a mean of 63 and a standard deviation of 3. And we're looking for the probability that a randomly selected unicorn X is more than 65 inches tall. Okay, let's take a look. So I want a normal distribution with a mean of 63 and a standard deviation of 3. I'm going to zoom in on that and compute the probability that X is, I can't remember what we were supposed to find, more than 65. More than 65. Okay, so 0.252 approximately. Now part B says if 9 unicorns are randomly selected, what is the probability that their mean height is more than 65 inches tall? Okay, so this one is a sampling distribution problem because this time we're looking for a probability involving a mean height, okay? In other words, we don't want the probability that a single unicorn is taller than 65 inches. We want to know the probability that an average of 9 unicorns is more than 65 inches. Well, the central limit theorem tells us that x bar is normal, so we can still use the normal distribution to compute this probability. Okay, the only thing we need to do different is we'll still use mu sub x bar, right? Mu sub x bar, by the way, is just the same thing as mu, which we've already said was 63. Okay, sigma sub x bar is sigma divided by the square root of n. Okay, so in this case, that's going to be 3 divided by the square root of 9, right? And then we're going to look for the probability that x bar is more than 65. Now, of course, in Desmos, there's no way to put an x bar in that space. It'll just say X. But when you write down your work, I want to see X bar there because we're looking for the probability the sample mean, X bar, is more than 65. So let's take a look. The only thing we need to change is the standard deviation, right? We need to divide by the square root of 9. So here I'm going to divide by square root of 9 and zoom in on that, but that's it, right? 0.023. 0.023. Okay, let's do another one. Okay, last example. As everyone knows, 22% of unicorns have rainbow mane. Common knowledge, right? Suppose that 150 unicorns are randomly selected and let X represent the number and P hat represent the proportion of selected unicorns who have rainbow mane. Okay, so X is the number and P hat is the proportion of unicorns with rainbow mane. Note that X is a binomial variable. Yeah, absolutely, right? Because with X, we're counting up the number of unicorns out of our 150 in our sample who have rainbow mane. Okay, so it's a binomial variable. Part A asks us to compute mu sub X, right? The mean of X, right? Where X is this binomial variable. Well, for a binomial variable, the mean is n times p. I think we've done this like 3 times so far in this section alone. N is 150. Maybe I'll color code it, right? N is 150. And P is 0.22. Okay, so we can type that into our calculator. 150 times 0.22 is 33. Well, let me change the color. Okay, part B asks for sigma sub X, right? The standard deviation. Well, for a binomial distribution, for a binomial variable X, right? Sigma sub X is the square root of n times P times Q. N we said was 150. P we said was 0.22. Now Q is always 1 minus P. Okay, so if P is 0.22, then Q is 1 minus 0.22, which you could type into your calculator if you need to, and that comes out to 0.78. So now let's feed that into our calculator. Okay, so that comes out to approximately 5.07. Part C asks for the probability that X is greater than or equal to 30. Well, X is a binomial variable, so I'm going to use the binomial calculator to do that. Binomial dist with n equals 150 and p equals 22%. And then I'll feed into it the probability X is greater than or equal to 30. Okay. Okay, and we're looking for the probability that X is more than, did we say 30, was it? So it looks like that's about 0.752. .752. Okay, part D asks for mu sub p hat. Okay, so mu sub p hat. P hat is the sample proportion, right? X was the number of unicorns with rainbow mane. P hat is the proportion of unicorns with rainbow mane. We want to compute mu sub p hat, and this is the formula for that, right? Mu sub p hat is just equal to p. Okay. And P, we already said, was 0.22. Part E asks for sigma sub p hat. Sigma sub p hat is the square root of pq over n. So that's going to be 0.22. Q should be 1 minus 0.22, 0.78. And then n is our sample size, right? N is 150. Okay, so we type that into our calculator. Now be careful when you're typing this into your calculator. The square root needs to go around this entire thing. Sometimes students will just put it around the top and not the bottom, right? They'll type it in like this, and that's going to give you the wrong answer. So that's not what you want to do. You want the entire thing to be underneath the square root. Let's see what we get. So that comes out to approximately 0.034. Okay, and then finally part F. It says compute the probability that p hat is greater than or equal to 20%, right? Greater than or equal to 0.20. Well, we're not going to use the binomial distribution for this because p hat is not binomial. P hat is normal, right? So we'll use the normal distribution. When we use the normal distribution, we have to put in something for mu and something for sigma. Okay, and the values for mu and sigma that we should use are these, right? So mu sub p hat is 0.22, and sigma sub p hat, well, you could put 0.034, but notice that we did some rounding to get that answer. So I'd rather just put in the exact value, square root of 0.22 times 0.78 divided by 150. And then we're going to compute the probability that p hat is greater than or equal to 0.20. Okay, let's do it. So normal dist 0.22 square root of 0.22 times 0.78 divided by 150. Okay, I'm going to zoom in on that, and then I'm going to find the probability that x is greater than or equal to 0.20. So that comes out to about 0.723. Okay, and that's it, right? So that's a review of sampling distributions. And then, of course, prior to that, we reviewed probability distributions, and prior to that, we reviewed just the basics of probability. But that is what we talked about in Unit 2. So good luck studying for Test 2, and I will check in with you in Unit 3.